Hello everyone, this is Ashraf Mahgoub, and today me and my colleague Karthick Shankar are going to present SONIC, application-aware data passing for chained serverless applications. This work is a collaboration between Purdue University, Carnegie Mellon University, Adobe Research, and ETH Zurich. Recently, PaaS or serverless platforms are becoming increasingly popular for complex workflows such as video analytics, machine learning pipelines, and genomics. In these systems, the cloud provider performs the administrative tasks on behalf of the user, such as scaling, scheduling, and maintenance. And usually, applications are represented as a series of stateless functions that communicate data with each other. And since functions placement is hidden from users, performing direct communication between functions is hard to achieve. And therefore, the state of practice to pass data between one sending serverless function to a receiving serverless function is through a remote storage such as Amazon S3. Now, before we discuss further the challenges in performing data passing between serverless functions, we give a quick example for a serverless workflow that is the video analytics application deck that we use in our evaluation. The application has 3 stages. The first stage, called split video, downloads the input video from remote storage and then splits the video into equally sized chunks. Then each chunk is sent to an instance in the second stage that's called extract frame that extracts a representative frame for that chunk and then sends that frame to classify frame, which performs object classification for the representative frame. And finally, the classification results are written back to the remote storage. Now, let's discuss the main challenges in performing data passing between 2 serverless functions. The state of practice technique to communicate data between 2 serverless functions or 2 lambdas is through a remote storage. This technique has its benefits, so as it allows for flexible scheduling, so the cloud provider can schedule the sending and receiving lambda on any VMs that the cloud provider chooses. The downside is that it increases the latency. And the reason is the data needs to be transferred over the network twice to and from the remote storage. Therefore, SONIC proposes 2 alternative data passing methods. The first we call VM passing. In VM passing, we limit the execution of the receiving lambda, that is lambda 2 in this example, to be on the same VM as the sending lambda. This approach leverages data locality since both the sending and receiving lambda have access to the same local storage. And it can become slow if I have multiple receiving lambdas to execute on the same VM, and the sum of their memory sizes doesn't fit within the VM at the same time. And at this point, we have to give up on the parallelism of the receiving lambdas, and they will have to execute in CS for this data locality to happen. And also, this approach becomes infeasible if we have multiple sending lambdas residing on different VMs. The second alternative that we propose, which we call direct passing, and in that approach, we copy the local state of the sending lambda to a new VM, that is VM2, before we execute the receiving lambda, lambda2. This approach is beneficial compared to remote passing since it copies the data only once over the network. However, it can become very slow if I have multiple receiving lambdas on different VMs and I want to copy the data at the same time to all these VMs. And at this point, the network bandwidth of the sending VM becomes the bottleneck and slows down the copying. In the next example, Karthick will show us in which scenario one data passing method can prevail over the others.
In this motivating experiment, we show that the optimal choice of the data passing method for any job depends on the DAG's parameters, like the input size or the degree of parallelism. We run LightGBM, which is a linear machine learning application with varying degrees of fanout in the train model stage, and we see that the VM storage method achieves optimal end-to-end execution time when the fanout is low. However, when the degree of parallelism reaches 3, VM storage requires executing all functions serially to make them fit in the same VM, which adds additional latency and makes direct passing superior. Finally, with an even higher fanout, the sending VM, or the PCA stage, faces a network bottleneck, which makes remote passing the optimal method. And thus, there is no single data passing method that prevails under all conditions. To dig further into the effects of network bandwidth, we run the same LightGBM application on VMs with different network characteristics. As before, with lower degrees of parallelism, direct passing is preferred over remote storage since it is faster to copy the data directly from source to destination as opposed to copying it twice over the network to and from the remote storage. As the degree of parallelism increases, however, there is a crossover point where direct passing is bottlenecked by the limited network bandwidth of the sending VM and causes remote storage to provide faster data passing since the sending lambda saves it to remote storage once and all the receiving lambdas can download it in parallel. This crossover point shifts to the right as we get better machines with a larger network bandwidth, as seen by m5.x large having the highest crossover point. Thus, the best data passing method not only depends on the DAG parameters, but it also depends on the VM's network bandwidth.
As we have seen in the motivating example, each data passing method becomes optimal in different cases, and therefore Sonic leverages a hybrid data passing approach in which it selects the best data passing method and the best lambda placement for each function and each edge in the DAG. First, we profile the DAG and monitor the following metrics: the memory footprint and the execution times for each function, as well as its input and output file sizes. We also monitor the fanout degree in each state. And then we use these parameters to identify the best data passing method and the corresponding lambda placement for each pair of sending and receiving functions in the serverless DAG. And as we have seen in the motivating example, the best data passing method is dependent on the DAG's execution parameters, which can change between one job and another. And therefore, Sonic needs to select the best data passing method dynamically with different jobs. This is achieved by abstracting the data passing method from user's code. And this is achieved through Sonic's API, in which it allows users to write and read the intermediate data files as if all the lambdas in the application have access to the same file namespace. For example, if an application DAG has an edge between lambda sender and lambda receiver, Sonic ensures that all the lambda receiver's files are present in its local storage before it starts execution. And therefore, the lambda receiver can read the files from the same path that we use to write the intermediate files to end the lambda sender's code. An additional challenge that Sonic needs to solve is how to avoid greedy data passing decisions whenever we are optimizing for the entire DAG. And one example is shown here in this slide for the video analytics application. And we assume that the VM passing selection between split and extract frame is the best data passing method between the two, because it saves the latency that we spend for either directly copying the chunks over the network once or uploading and downloading through remote storage. However, the downside of using VM passing between split and extract frame is that the resulting frames will be residing on just one VM. And if we want to use data locality between extract frame and classify frame, then we will have to run, again, all the classify frame instances on the same VM. And because classify frame requires more memory, we will give up on the parallelism and they will have to execute in series. A better solution would have been that we pick a direct passing method between split and extract that is less optimal in terms of latency for this particular stage. However, that will allow us to spread the classify frame instances on over as many VMs as we need to run them in parallel, and that will lead to a globally optimized latency and the cost for the entire DAG. Now we give an overview for Sonic's design. First, the user provides Sonic with the DAG definition, which includes the definition of each stage in the DAG, as well as the executables and the data dependencies between the functions. The user have the option to provide Sonic with a series of inputs that vary in their sizes. Then the next component in the design, which is the online profiler, uses these inputs to profile the DAG multiple times and monitor the performance metrics that we mentioned earlier, given the job's input sizes. And these prediction models are used in our online manager. The online manager observes for each new job what is the new input size, and based on that, it applies its Viterbi optimizer to identify the best sequence of lambda placements and data passing methods so that we minimize the latency and the cost for this particular job. And now we define the baselines that we use in our evaluation. The first baseline is Open Lambda framework and using S3 as the remote storage. For this particular baseline, we use a new VM for each Lambda in the DAG. Open Lambda is the framework that Sonic uses as its base framework. However, this baseline is just the vanilla Open Lambda without any component of Sonic. We have a second variant of Open Lambda where we are replacing S3 with Pocket as the remote storage, and we use Pocket's default storage tier, that is the DRAM tier. We also compare to Sand, and Sand always leverages data locality by allocating as many Lambda functions as possible on a single host. We also compare to AWS Lambda, the commercial platform, and we also compare to a variant of Sonic, that is Oracle Sonic, in which we assume that we have fully accurate estimation of the DAG's parameters. And we also assume that there is zero latency for data passing between any two functions in the DAG. In this figure, we compare the end-to-end latency and the cost for Sonic versus the baselines. First, we notice that Sonic achieves higher performance per dollar, that is the latency normalized by dollar cost, compared to two variants of AWS Lambda, that is S3 or Elastic Cache Redis. And the reason is because of Sonic's optimized Lambda placement decisions and data passing, hybrid data passing decisions. Compared to Sand, Sonic achieves 1.8x better performance per dollar and lower latency. This is because Sand always forces data locality across the stages of the DAG, while Sonic can vary the data passing selection across the stages of the DAG. Compared to Open Lambda, either using S3 or Pocket, Sonic also achieves higher performance per dollar, which again stresses the benefit of our hybrid data passing selection method. Compared to Oracle Sonic, we noted that Sonic only loses by 19%. Recall that Oracle Sonic uses the fully accurate DAG parameters and also assumes zero data passing latency between the stages in the DAG, which shows the significance of the accuracy of Sonic's performance prediction models.
Sonic uses the job's input size to predict the DAG parameters like intermediate chunk sizes. This allows us to generalize without looking into the application itself. However, in some applications, these parameters also depend on the input content. For example, intermediate chunk sizes in the video analytics application vary based on the video bitrate or video quality. We run an experiment to evaluate Sonic's sensitivity to input content by executing it with test videos that are from different content categories from the training videos. We collect 60 YouTube videos from 5 different content categories which have varying bitrates. We compare Sand and Open Lambda plus S3 to 3 different variants of Sonic as well as an Oracle variant. The first is same category, where the test and the train videos are from the same category. The next is all categories, where we have training videos from all 5 categories. We also have the unseen category, where all the training videos are from the news category, which has a 25% lower bitrate than the videos in the sports category on average, which is the test category. Finally, we have the zero error variant, which is our Oracle, that has perfect knowledge of all execution parameters. The same category variant naturally performs the best out of the 3 Sonic variants due to its low prediction error. In the all categories variant, we see a small performance reduction of 8%, while the third unseen category variant causes a further performance reduction by 19% due to the error in predicting the fanout degree and the intermediate data size between split video and extract frame functions. All 3 variants, however, still show a significant gain over Sand and Open Lambda plus S3. Thus, the higher the difference in features between training and testing data that impact compute time or intermediate data size, the lower the performance of Sonic. One solution to this limitation is to cluster the jobs based on these critical features and train a separate prediction model for each cluster.
Finally, we evaluate the scalability of Sonic, in which we execute Sonic with a hybrid of workloads. We use 3 workloads. The first is map, reduce, sort, and the second is LightGBM, in which we train a set of decision trees, and the third is our video analytics application. We compare Sonic to Open Lambda plus S3 and Sand, while we vary the number of concurrent jobs from each application between 15, 30, and 60 jobs. We notice that Sonic outperforms both baselines in performance per dollar as well as the raw latency, and which stresses the benefits of jointly tuning the lambda placement decisions, and as well as the hybrid data passing selection that Sonic performs to minimize the latency and the cost. In conclusion, we showed that data passing between serverless functions is a challenging problem. In this paper, we studied 3 different data passing methods and showed that there is no single method that prevails under all conditions. Hence, that motivated our design of Sonic, that is a dynamic and hybrid approach to select the best data passing and lambda placement decisions for the entire DAG to minimize its end-to-end latency and the cost. And with our evaluation, we have shown that Sonic outperforms all baselines in terms of cost, normalized latency, without sacrificing the raw latency. In our ongoing work, we investigate how to handle content dependence in application DAGs and how to handle dynamic control flows in serverless workflow. At this point, we conclude our talk. Thank you so much, and we look forward to answer any questions.